No, I mean, you should see what I see. It's really funny. That doesn't concern, of course, the first row, just to make sure they don't incite anybody. Okay, so welcome back to the second session today. We're still tackling the topic of advanced simulation, and a lunchtime simulation with Bilge and Steiner actually led us to paraphrasing the problem of simulation in the following way. We are ahead of the future. The only thing we don't know is whether the future will follow us. So having said that, I would just like to say that we have 3 presentations this afternoon. Around 4 o'clock we will take a very brief tea break. So I would like to ask the end not to simulating a symposium. So we will have 3 presentations this afternoon. As we go along, we will introduce the speakers. 4 o'clock, we will have a very short tea break. So I would like to ask the audience to really make sure that we can start 15 minutes after the last presentation with the final podium discussion for today. And having said that, I would like to introduce our next speaker, Professor Jeronimides. Most of you already know him. He's the chair of the Center of Biomimetics at the University of Reading, and also teaching here in the Emerging Technologies and Design program. And yeah, having said that, I could either start his presentation or let him have to go.
Good afternoon, everybody. As Michael said, some of you have seen probably enough of me. Again, very happy to be here and get involved in these kind of things, because I think, as we were discussing over lunch, in fact, most of the problems that we are trying to address are really, to a large extent, a problem of communications between different disciplines and different ways of thinking. What I'm going to present is really a bit of a personal view, if you like, about what modeling and simulation is about. Everybody has got his own view, because we are, to some extent, conditioned or preconditioned by our own professional activities, and in any kind of branch of engineering, material science, social sciences, meteorology, whatever you like, people are using modeling and simulation tools more and more. So I'll take you through what my own view is as to what simulation and modeling should be, what is there for. I'll give you a few examples. Again, some of you may already see, but I don't want to go too much into the details of those. It's just, again, to give you some idea of what one can get out of it. There is no doubt in my mind that, as far as I'm concerned, I found more and more that modeling and simulation are really tools which help me to think. And that's why I put lateral thinking and creativity as the second title, or second part of the title, because it is a way of exploring dimensions that normally, by normal means, would be difficult to do. In many ways, mankind has been doing that all along, but with slightly different tools. And of course, the modern computer generation type simulation does offer another dimension in terms of not only the complexity of what it can deal with, but of course in terms of the speed at which it can do with it as well. So, let's see if I can get that. That's the main structure of the talk, okay? And as I said, the first thing I want to talk about is really to try to make a point about the difference, perhaps, or my perceived difference between between modeling and simulation, and of course reality, which is what we are trying to attach these things to. Some of the tools, the ones that I'm familiar with in my own profession, if you like, all along, not as a specific topic, I will raise questions as to what are modeling and simulations for. Some examples which may relate to the generative design processes, which is the theme of the talk, and a few conclusions. Right, well, you're all familiar with that, which is the map of London Tube. And then you can ask yourself, well, what is this? Is it a model? Is it a simulation? Or is it a reality? Or perhaps it's a virtual reality. It does have certain features, which of course correspond to reality. There are other features which really are a million miles away from the real reality of what the underground system is. Okay, and it was brilliant from the man who designed that now. I can't remember his name off the top of my head now. Who decided at the time that rather than make a detailed copy of the pattern of the railway, he decided that he thought about it. What are the crucial points? What people want to know? In many ways, modeling or simulation is about that. What people do actually want to know. Ask yourself the question before you start thinking about the model. So if you look at this map here as an example, okay, well, is the geometry right? Well, the geometry is totally wrong. The distances are far from being real, even in scale. The relative distances are wrong. Everything is wrong in geometrical terms. So it's not an exact map of the London Underground system. So the question is, well, what then is good about it? Well, let's go and see something else. I mean, are the colors of any use? Well, they are just labels to identify different bits. And I bet you sweet life that if you go into London nowadays and tell someone that you have taken the yellow line as opposed to the circle line, 99% of the people will know what you're talking about. Because we have now an identification between the information in the model, if you like, and the reality outside. And we can make a kind of switch between reality and model. So the colors are not right either, but they do add information because they represent simply a separation between different lines. Well, that's useful. What about connectivity and topology? Well, that is right. I mean, what you want to know is where you're going to have to change trains, okay, and what kind of tube station you want to go to. That's the important information about that map. Nothing else matters. Okay, so when you come down to that is the essence of that particular model. Okay, and in that sense, I call it a model, of course. It's not a simulation because nothing is moving there. The trains actually do move. I'm sure that nowadays one could create a computer-based map where the trains actually do move as well. So, but it's an example, as I said, of what I think models should be there for. It's really to extract the information that you need at the time. And of course, as you ask for more information, then the complexity of your model may change at the same time. But models have got their own level at which they are appropriate, and there is no point in complicate life unnecessarily. I want to just go very briefly through some of the tools which have been used throughout history in simulation, because they really do add a little bit about what people have been trying to get out of the models. And certainly the first type of modeling, if you like, was done by drawing things on paper, drawing things on sand. And this is the drawing from Leonardo da Vinci of his ornithopter. And what the function of that drawing is primarily, essentially, to give some idea of the relationship between the different bits which make up that particular object, okay? The relative connections, the overall geometry, and some idea of the dimensions, perhaps, if you add some kind of scale. Again, it's a far cry from the reality of what happened afterwards, but it is the thinking tool. It is nothing more than a thinking tool. It's there that you use your pencil and you sketch and you erase something because you're not quite happy with that and you replace it with something else. So it's a very interactive type of modeling. And again, as we go along, you will see where the difference between, or the transition rather, between modeling and simulation comes about. So that's the first one. Mike will certainly vouch for that, people were building wooden ships, made physical models. Okay, if you go to National Maritime Museum, you will see some beautiful, absolutely fantastic models of ships, which were not there as works of art. Those were working tools of the shipwrights. Those were the tools they had available in order to, again, try to understand how the various bits had to come together, try to get some idea of the scaling and the scaling problems associated with building such a complex thing. So again, physical models, and we still do use physical models, and it's not surprising, and I go back to when I was here a few weeks ago, or perhaps it was last summer, I can't remember, a long time ago perhaps, where I was looking, no, it was here, with the current students were showing some of the first ideas about their projects. And it was very interesting to me because in many ways, most of them, in fact all of them, did actually build physical models, okay? Because a physical model has got some kind of tangible reality that you can, again, use to explore your design space. So that's physical modeling, and as I said, you can make it as complex as you like, but again, it's important to understand what you're trying to get out of it and what, again, the limitations are. It's still modeling as opposed to simulation, because there's nothing which is simulated there. These things were not put in water to float them, okay? It was just a piece of tool for putting bits together and decide dimensions and things of this kind. Of course, the other type of modeling which does exist and still with us is mathematical models, okay? Now, call them equations, call them whatever you like. Okay, they have also a function of representing some element of reality, and they can be as complicated or as simple as you like, at least in terms of the visual aspect. That doesn't mean that what they imply behind is simple. So you've got things like E equals mc squared, Einstein's relationship between energy, mass, and the speed of light. And in relation to that, okay, this is a model. I mean, we don't know whether this is our description of what we see or what we measure, and for the moment is nothing but a model, okay? And it is a usable model even in that form, because we can put numbers in there, okay? If you know the mass of something and you know the velocity of light, okay, you can do the calculation and you can get the equivalence in energy that you could get out of that system if you separate all the atoms and all the electrons from each other. So it is a model. It's got a function in terms of representing some perceived reality. It's got another function, of course, which is important in any modeling, which is to be able to make predictions as well. Okay? So the model has got an element of description of something, but a good model, if you like, is also something which can help to predict something. So that's one. Okay, since last time we spent a bit of time with buckling with one of the students. Well, that's another equation. Now that one looks horrible. Okay, it's certainly not obvious what it does. The one above is actually interesting because it's very intuitive. Okay, as I said, it doesn't really require an awful lot to understand what the message in the first equation is. The message in the second equation is not very obvious at all. Okay, and this is the equation which governs the buckling of plates and is used by engineers, etc., structural mechanics and whatever, because we want to know when these things do change in terms of their behavior. So that is, again, is a model, but is a model which is not the same as the one above, in that that is only part model, in the sense that you can't get any information out of it unless you go a few steps beyond. And of course you can do that, not necessarily very easily, but we can do that. And this is now the transcription, if you like, of the model embedded in the equation into a reality which is more amenable to be understood, interpreted, and used. We need actually, and it's very interesting, because I think another aspect of modeling that I'm sure is true, but as I said, I can't sort of put anything more than my feeling about that, is that we as humans really do need and rely very heavily on the visual information. And so an equation may be very nice for some, but it doesn't have the visual information level that is necessary for us to go one step beyond. So when we, even in engineering, when we do solve that equation up there, okay, we don't just look at numbers, then we try to translate those numbers into something that our eyes can interpret more effectively. So top right there, what you've got is the model again. This is the plate under end loads, which is going to buckle. Okay, A and B are the two dimensions of the plate. All these things go into that box where the equation is, with additional bits of information which relate to the thickness of the plate, the material properties, the boundary conditions, how the edges of the plates are held or not held. Okay, then we solve that, we put some numbers in, and then we can draw some additional models, if you like. Yet again, a different type of model, which are the set of graphs which have got down there at the bottom. And those graphs are there really for the purpose of helping someone to design something. They are there to use the model in its predictive capacity now, as opposed to just its descriptive capacity. So what you have there is a series of curves, and it's actually quite interesting because it makes you think about all the things when you see that thing in that form, and it's much more difficult to see it inside here. These are a series of curves which give you the load at which the plate will buckle as a function of the dimensions of the plate. That's the ratio of A to B. So one represents a square plate, and these are rectangular plates of different aspect ratios. And this is the number of waves in which the plate will buckle. I'll show you that in a moment. And you can get plates which buckle with 1 wave, 2 waves, 3 waves, 4 waves, 4 waves, etc., etc. Now it's very interesting because you can see that a plate of aspect ratio 1 will buckle at k equals 4, okay, which is here. So that's the minimum load. Now if you want to prevent buckling, of course, what you want to do is to increase the load at which the thing is going to collapse. So you want to move away from that point. Now if you go as far as number 2, okay, an aspect ratio of 2, so A twice as big as B, you find that you are exactly in the same position as you were before. Okay, so that there is no advantage in making a box, say, or a plate size 1 by 1 or 2 by 1, you will get exactly the same buckling load. But lo and behold, the important thing is here, because here is somewhere in between 1 and 2, and if you want to increase even marginally, not by much, because you are moving only from about 4 here to about 4.5 up here, but in a lot of applications that difference is significant. Okay, well, if you want to design a box which resists buckling better than this one and this one, you go and choose the dimensions so that in fact it is just there. Okay, so that allows you to carry more load before something happens. Now all that, obviously, we can sort it out by talking, by looking at these graphs and whatever not. Now if you look at the next slide, okay, well this is now a computer simulation of the behavior of that plate. Okay, so the plate is there on top and is actually an aspect ratio about 4 to 1. Okay, and computer models, computer systems provide you with means of calculating the loads at which the different type of buckling occurs. The one bottom right is one of the lowest mode with 2 humps, if you like, one popping out and red popping out outside the board and blue going in. And the one on the right is what is called a higher mode, which requires a higher load to be produced. And depending on, as I said, a number of parameters, we can force the plate to go into any one of those. There is no question that this is more appealing than the equations that you had before. Okay, but of course the problem arises is, how do you know that this is correct? Okay, so simulation. And now we are moving towards simulation rather than modeling. Okay, simulation does imply also an element of checking. How do you know that what you simulate or you model is right? And that, unfortunately, is often forgotten, and I think is pretty crucial, because although a simulation can give you a number of ideas, and as I said, if you look at it in that role, stimulation of intellectual ideas, well, that's fine. That's just, as I said, one function. If you want to use it as a design tool of any kind, then it is important that you get some idea how accurate what this thing predicts actually is. So, okay, this is now making the transition. In many ways, this is still not a simulation. It's still in the realm of modeling. Okay, it's a more sophisticated type of modeling. There is no additional information here that there wasn't in the previous slide. It's just that the picture is easy to interpret. And the real change between the model and the simulation, the modeling and the simulation, is when you move from static systems, if you like, to dynamic systems. When you have things which now cannot be solved because of their complexity, because of the complexity of the system, or because of the complexity of the interactions of the system with the environment, okay, then traditional methods is not a question of them being better or worse, is that they are not just capable. Okay, there are limits to what we can do with equations. There are things which we cannot put into equation, or even if we could put them into equation, we wouldn't be able to solve them anyway. So now something else is happening. Now we are using tools which are numerical tools now. They are still handling numbers, but not in the same way as an equation. And those tools are allowing us really to get into the area of simulation, where now we can look at the behavior in a dynamic sense and not just in a static sense. And this is the, again, some of you have seen that, but again, it's a good example, okay? This is the physical model. Well, this is the simulation of the physical model that Sylvia and Jordi did last year for their project, or part of it anyway. And for those who don't know what that thing is, it's part of a structure where you've got a number of elements which are connected at these points, and these things here are essentially actuators. They are things which can push or pull, okay? And one of the interesting things about this type of structure and the interaction between the various bits, of course, is the fact that because the three strips of material here, 1, 2, and 3, are connected at these points, then when you actuate these things, in other words, when you make these things either longer or shorter, the mechanics of the system forces that thing to curve. And this is its normal position, and this is its curved position, where these things here are getting longer, and these ones are not moving. So the red ones are elements which are stretching, the blue ones are elements which are at the same length, and the coupling between the various bits forces the system to curve. So you can have a structure, I mean, their concept of their structure was to have something where, according to environmental condition, according to how they wanted that to interact with the environment, it might be beneficial to have something where you can change the shape according to your needs or demands. And they built a very a physical model in the first place. They did a lot of drawings. They reasoned about the thing. They came to a number of conclusions. But then that wasn't enough, of course, because at some point, if that thing does have to become a reality, then what you need to do is to add these other bits of information which will form, if you like, or provide the transition between the virtual world and the real world. Okay, when we talk about actuators, well, what kind of force do you have to put in there? Okay, what kind of things can actually produce that force? If you want to stretch or bend these elements here, well, what kind of material is best suited to do that, so that you can achieve the levels of deformation which are needed in order to give you the behavior that you want? How limited may you be by the fact that some materials may deform elastically up to a certain point, others may not be able to deform elastically, and you may be able to deform the thing only once and will never come back again because the materials have exceeded their yield point. So there are a lot of questions like that that the modeling or simulation can help you with. And the more complex the structure is, the more really one is talking about simulation as opposed to modeling. Because you're not just looking at the static behavior, we're looking at the dynamic behavior of the whole lot. So interestingly, we went one step further because they actually did some calculations of that. Okay, this is just to introduce the next part, which is really to do with the dynamics of systems, okay, and patterns. And to me, again, what is important in a lot of simulation processes is the fact, as well as I said, making predictions, helping with expanding, if you like, the design universe, is the fact that it's a lot of simulation techniques which may come from completely different directions are extremely powerful in creating patterns. And this is some work we did with one of the students, in fact, just off the cuff, about a week ago, simply to look at where were the patterns of buckling in a cylinder. Actually, those are the vibration patterns of the cylinder. Okay, the interest was not in designing cylinders. The interesting thing to me was the fact that there was a physical environment which was producing shapes which were interesting. Okay, and then one could think about the interest of the shape and move it out of its original context, and we something else with it. And again, this is something which simulation should promote rather than confine. In fact, Mike did mention it at the time. Okay, this is an interesting design. This is a can of something, and you can see that the can hasn't got straight walls as it normally has. In fact, it's got the walls which are closely related, not exactly, but closely related to the pattern of a high mode buckling pattern in a cylinder. So the idea was to make the can already in the buckled shape, okay? And then you may argue, well, what's the advantage of doing that? Well, the advantage of doing that is if you do it in a buckled shape, which is not the normal one where the cylinder with those dimensions will want to be, is going to find it more difficult to actually buckle where it wants to go. So you are simply making life more difficult for the system to go to the minimum energy configuration, which normally corresponds to the buckle. So by having this patterned surface, the advantage was for the same amount of material, these things could carry a higher vertical load. And that's important because these things are stacked on top of each other in storage and in transport, so they have to have an intrinsic resistance to collapse. And so either you can get a higher collapse load for the same amount of material, or you can get the same collapse load, but then use less material to achieve the same result. So that's an interesting thing. And there's no question that the process by which people arrived at that was a combination, as I said, of intuition, common sense, and some kind of simulation. Back to the model of Jordi and Sylvia again, because one of the interesting things about that model, of course, is that depending on what configuration it is, at the end of the day, again, if it's going to be a useful device, you will have to carry some loads. And we did what they could do experimentally on the one hand, and then I agreed to do a kind of simulation again of the response of the structure to an applied load. So this is again that beam, this time in its neutral straight configuration. You just apply a load at this end, and then you add loads until something happens. And then what happens, or one of the things which can happen is this, okay, that one of the elements, this one here, actually does buckle. Okay, you may want it to buckle, and there are some advantages actually allowing at least part of the structure to buckle in order to get into a shape which would be impossible to achieve without the large displacements that the buckling requires. But on the other hand, this kind of tool is useful because if you want to, on the other hand, prevent the buckling, then you know where is the problem. And then you can go and solve the problem only where it matters and leave all the rest as it was. So those are simply examples of, again, what you can do with something which now, as I said, is a little bit more than just a model in a static sense, because again, what we're trying to extract here is really the dynamic dimension of the system. You have seen some of those, and half of you at least have seen these things, but for the other members of the audience, this is some work that we were interested in, still interested to do. This is to do with making actuating devices which are based on muscle type action. And the real objects consist of a braided tube made of fibers, and inside the tube is a polymer material which can swell quite a lot when it's exposed to water. It can increase its volume by 500 to 1,000% of its original volume. So it's got this enormous capacity of swelling. And the idea behind it is to be able to use that kind of mechanism for producing, as you say, as you can see, sort of muscle type structures. Okay, so this is your relaxed muscle. You put that in water, the water gets into the gel swells, and the confinement of the gel within the braided structure forces the system to lift the weights, which is more or less how your muscles work. Not in the detailed molecular level, but at some intermediate structural level, that's essentially what goes on. Okay, we need a simulation tool because making these things and measuring things is actually very, very time consuming. Okay, so if we can produce some simulation tool which allows us to play around with the various variables that that are involved in designing these things, then we can save ourselves an awful lot of time in order to be able to make use of the information without every time having to create a physical model and test the model. Eventually, in reality, we need always a check back by having some physical model to verify the lot, but we can go a long way without that. So the interest on this one, okay, this simulation of this straightening thing is not what I'm going to show you, in fact. What I'm going to show you is that with the same object, we can do other things which may be useful in the context of applications such as robotics, for example, where we want actuation at low mass. And this is, again, the technique uses finite elements, which is nothing special, okay? It's just a way of simulating and calculating things. And this is the braid, this inside is the gel, and in this particular design, okay, what we wanted was to induce a bending of the tube as well as the elongation. And this is just the simulation of that process. Now, it's a simulation rather than a model because it's not just the geometry which is right, okay? The geometrical elements must be correct, okay, in terms of the diameter, the thicknesses, or whatever, the mechanical properties of the various components, the characteristics of the swelling of the gel, all those are physically measurable numbers, and they can be put back into the model. The change of shape is purely a geometrical effect, but the change of shape is only one of the parameters that we are interested in. Okay, by how much change of shape, of course, is important, but we need to know also what kind of pressures are generated inside in order to get to that change of shape, because if these pressures are too high, of course, they can make the braid collapse. So we can play around, and simulations of this kind can take from minutes to hours to days in some extremely complex cases. And the higher the level of complexity, of course, the more time it's going to take to get the answers. So one of the interesting things, okay, is that, again, and this is to me also an important concept of simulation, is that simulation can help to build bridges. You see, the reason why this thing is bending is exactly the same reason why this thing here is bending. Okay? They don't look like the same thing at all. Okay? The bits are completely different. The dimensions are completely different. Everything is completely different. The only thing which is common is the fact that you've got an interaction between different parts, which are, when you force one of the parts to deform and not the other, or the other is passive, the connection between them, if you like, produces as the natural consequence of that the curved shape. But here we're doing exactly the same thing. This model here and the physical equivalent of that is simply something where the bits on this side are not the same as the bits on this side. So across the diameter, if you like, you've got mechanical properties of type A on one side, mechanical properties of type B on the other side, which we can introduce very easily in manufacturing the physical model, even more easy to introduce in the model. And then we just increase the pressure, which is the equivalent of your actuating devices in the other model, and the interaction, and this is the important point, the interaction between the parts is what creates the change of shape that you want to do. So it's extremely useful because then you can connect different things together and you can try to exploit these things. So it's the same principle, as I said, as the George's and Cindy's project. Two different sides with different behavior, forced to act in concert. So it's a forced relationship. Like all forced relationships, of course, you pay a price. And the price is that if you want that kind of behavior, you're going to have quite high internal tensions and compressions to the system. So information is required not only of the change of shape, but what are the implications internally in the system of that change of shape. As a mechanical engineer or a structural engineer, that's important because you want to make sure that the thing is not going to fall apart. This is the same thing, but this time what we wanted to do was to induce twist along the axis of the tube, and there are reasons why some type of actuation for robots would benefit from having things which can turn without having to have the complexity of gears, wheels, stepper motors, or whatever else. So this is exactly the same thing as before, where we have changed another parameter. We have added an imbalance in the braid structure to make the left-hand side different from the right-hand side, but in a circular form this time. You've got two helices going around. The left helices and the right helices are not the same material, not the same properties. And the natural consequence of that is that the thing is going to have to twist. One of the interesting things that came out of the model, which in fact we should have anticipated, is that this thing, because it's simulating the swelling of the gel, at some point stops swelling. Okay? In other words, being a gel which wants to expand to maximum volume, and you can relate that to the structure of the braid, then you do have a position where the thing cannot move from that position anymore, because whichever way it will want to move, it will have to decrease its volume. And it can't do that if the gel is fully swollen, because it's virtually incompressible. So again, something which then we went back to and cross-checked, but it came out in the first place in running the models and finding out that the models were actually stopping deforming at some stage. And the first time we thought there was something wrong, convergence problems, divergence, whatever, and then we realized that the model was actually physically doing the right thing, stopping when it had achieved a shape of the container where the maximum volume was reached. So some conclusions, just about on time, I think, in all that. And those are, again, the roles, again, of what models and simulations can do. I mean, there is an element of verification. Does it do what it's supposed to do? I mentioned the Millennium Bridge because it is one that everybody's familiar with. Okay? I mean, it is certainly true that that thing is oscillating at a particular frequency, or did before we put the dampers in. Okay? The question is, was that its well, the primary function, of course, was to carry people across, and it did that very well. That wasn't the problem. The fact that it was oscillating a particular frequency was a nuisance more than a real problem. However, if people don't like that, you have to do something about it. Now, was that predictable? Well, I believe that it was predictable, but again, in order to predict something, the first thing you have to do is to ask yourself the question as to what is that you want to know. The second, more important aspect of modeling and simulation is really what I call the extension of the design space. Okay, when I've got a model on my computer, I can play games. I can try to change dimensions. I can try to change thicknesses. I can try to change mechanical properties. And that gives me sometimes opportunities to look and to witness, if you like, events which would be almost impossible to do by normal means because we haven't got the time to build physical models with 100 different materials, 100 different thicknesses. And as I said, in simple systems we can use the equations. In complex systems, we really need to go back and use the simulation. So the extension of the design space is really very, very important, what I call the what-if approach. What if I do that? What's going to follow? Then the next step, which I think is more or less what the theme of the meeting is, which is really to look at these complex dynamics interactions and whether they are complex dynamic interactions within the structure, the material, the object, or whether they are complex dynamic interaction between objects and people. It doesn't matter, okay? We're talking about extremely complex systems. And again, simulation is a tool simply to get a grip on what controls these interactions and how they sort of feed onto and cross-feed onto each other. Okay, an example where both the structure and the environment are changing are some of the things that people are working nowadays, which I mentioned in one of the lectures, conformable wings for airplanes. Okay, a conformable wing is designed to interact with this environment because the environment is changing and you want the wing to change as a result of the environment changing. So you've got a complex system there where you've got now a structural element which is coupled to an environment via a bunch of fluid mechanics. Okay, extremely complex problem, and a lot of people are working on that, and I'm sure that millions of hours of simulation are being used in order to get some answer to the problem. So, and the last bit, which comes back to the beginning, okay, which I think again is important, is that it's a way of getting out of your cages. Simulation allows you to explore space, which your normal environment will not allow you to do. So it's again not the same as the extension of design space, because they're just an extension on the basis of what you already have. This is really going somewhere else altogether. And in that sense, then the modeling or the aspects of modeling which are coming from other disciplines are really very, very important. And if you talk to, I guess there was someone from meteorology this morning. We have a big department of meteorology Reading. They are using millions of CPU units per day. Okay, I mean, all the things that we're beginning to hear, like chaotic behavior of chaos, things of this kind, are essentially nothing more than modeling and simulation of complex systems, where interactions between parts, either in a given time or in a given time frame or in a given space frame, are very, very complex. So when I say about short and long range effects, what I do mean in terms of physical or scale, or in terms of a time scale. Okay, what are long-term effects in relation to time? Or what is the effect of a disturbance at this point of the structure? What is going to happen at the other end if I can predict it? And this is a very, very complex thing. And it may happen instantaneously, and it may happen over a period of time. So that's the summary of what I wanted to say. And thanks very much. Yeah, that's fine.
Okay, we will do the question part when we start the podium discussion. After we have three speakers, and let's see if we get through the presentation before we start the
conversation. Let everything plugged in and take it to this connection. So take this one. Okay. As this next speaker, I would like to introduce Andrew Nicholson. And I'm going to do it very briefly because I think we're going to have another very interesting talk to see, especially in relation to George's talk. Andrew is an associate fire engineer with Bureau Happold-Fedra, which stands for Fire Engineering, Design and Risk Assessment. And he is currently working on projects including the Wimbledon Center Court, Battersea Power Station, and new proposals for the Millennium Dome. So I think we're going to see some very interesting case studies and insights into ways of simulating, modeling and simulating, on the one hand, quite mechanical and structural systems, and on the other hand, actually human behavior that starts to interact with these already quite complex things. So I'm really looking forward to that talk. Thanks.
I think the good thing about my presentation is everybody else seems to have explained what simulation and modeling is all about. So I don't have to go there really. You all know what computational modeling is and simulation, and there's a good presentation just then showing you what the limitations are and what we expect to find out of modeling. What I want to do really is show you some case studies of where we've applied some of the computational modeling that we use as engineers in the built environment. I'll give you a quick introduction into where I'm from, what we do, and then I'll talk about some practical applications of evacuation modeling, smoke and fire spread, some structural fire modeling, and then I'll give some case studies towards the end. Now, I work for a company called Bureau Happel. They're a multidisciplinary consulting engineers, so that means we deal with a whole range of engineering disciplines, from facade engineering through to mechanical and the traditional structural engineering. But I work for the fire engineering division. And what that means effectively is that we try to design buildings or aspects of the built environment to accommodate situations where a fire might occur and where there might be loss of life or loss of structure, or sometimes, which is becoming more common, loss of contents or business continuity, such as maybe museums or banks, which contain obviously lots of valuable money and assets. Now, I get to work on a whole load of different projects, and I do mundane things like help architects work out how to develop their fire strategies, which is probably 90% of what I do throughout the day. But when we work on some of the high-profile projects, some of the complex projects where actually the design guidance that we all are supposed to use to help us develop fire strategies is just not really applicable, then we use the science and engineering of fire engineering to understand if we can develop our strategies further. So I'm probably the type of guy you'll phone up when you're designing your huge big structure with huge atria in there and with whole loads of people in there, and you ask me how we're going to develop the evacuation and how we're going to get compliance from the regulations. Not just in the UK, we do this all over the world. So what I'm going to do is I could talk about whole aspects of fire safety, but we have three particular models which we use to assist us in determining and understanding the eventualities from fire. Now, the point I will make first of all is that computational modeling is just a tool that we have as engineers at our availability to further understand complex situations, and it's never the final answer. We should do a whole load of sensitivity analysis to come up with situations that we need to test and interrogate. So it's really just another tool that we have, and it's just as good a tool as our initial thoughts. So as an engineer, I obviously have an idea of how things might behave to start off with. Then I might do some hand calculations to further validate that. Then I might, if necessary, go on to computational modeling, which validates both my hand calculations and my initial understanding. And then actually, if we really need to get further understanding, we'll try and do some real simulation, some real live testing. Now that can be quite difficult, obviously, with people and fire. The last thing we want to do is throw a whole load of people into a burning building. So we have to generally look at our practical applications, more to do when the people aren't around. But what I'm going to look at here is building Exodus. Now this was a model that's been developed by Greenwich University, and it's a mathematical model to understand the realistic movements of people in building situations. Professor Gallia is probably one of the leading experts in the world in terms of fire safety and evacuation of people. And I work closely with the group over there to develop the model and to help them understand as a day-to-day user how the model should be developed. It's quite interesting how we validate these models, because obviously it's just a mathematical program and we need to make sure that it's having some representation to real-life situations. So we have to look at real-life situations and try and understand what happened in those types of events. And actually one of the interesting first validations of the model was a whole load of students that were given £20 in a building, and the guy that got out first got £50, and they weren't told where the exits were. They were all thrown in there, and they were just had to behave upon the fire alarm system. And that's how we started to validate these models in the early stages. It's progressed a lot better now, and we've got some better techniques of validating our models, but they were some of the early situations. We support the university, which I've just mentioned, and I was principal author for the new British standard, which helps us all design means of escape in buildings. And historically, means of escape is based on, like anything in legislation, is based on English law, or things that have happened in the past, and changes that need to occur in light of those situations. And that's the same for means of escape. Actually, the reason why we have limited distances to get to a fire exit or to a place of relative safety is based purely on historical information on fires and bears no resemblance to any science or engineering that we know today. So what I certainly did in our practice, we wanted to develop the means of escape side of the British standards, but put some science and engineering behind it. And we used the computational model to do a lot of what we call parametric studies in the engineering world, which really is just a whole load of different tests that we do on the same building, and sensitivity analysis, really. So that's been some of its applications. I was told to keep it quite technical in terms of how the models are set up, but I'll whiz over this because I think the most important aspects of what I'm talking today are the case studies and what we actually get out of these models. So the reasons we use them is that we can get an understanding of the movement of people in these buildings a lot better than we could do with simpler correlation-based models or the mechanical models that we use, i.e. just the movement of people based on a speed and a distance. What this actually looks at is the interaction of people and building, people and people and fire situations. We can look at crowded situations, we can look at merging of flows, which is often a particular incident we get on a staircase where people are coming down a stair and we get a whole load of people coming in on another floor. And what's the dominating factor? Is it the people already on the stair which command that flow, or is it the people trying to get in on the floors below? And the answer is people don't know that question, the answer to that question at the moment, and we're still trying to understand what the situations are with mergings of flows. We have a professor from the Building Research Establishment, Professor Purser, developed the toxicological model, which has been inputted into the evacuation model, so that we can start to record products of combustion such as carbon monoxide and hydrogen cyanide in their parts per million. And we know what the tenability criteria are on occupants, so we can start to see that if the parts per million of hydrogen cyanide is at a certain level, that we know people are going to be incapacitated before they get to an exit. And that's really what we're trying to understand here, get a better understanding. And we can look at impatience, obstacles that might be in the way. The actual people that we use, we can put 22 different characteristics for each individual, from dexterity to age, to drive, to weight, to gender. We can actually prescribe particular groups. So if we're looking at whatever, we might be looking at a school, so we can slow the movement of people down to reflect the speeds of maybe children or people with impaired mobility in disabled situations. What's cool about it is that we can take your drawings straight out of DWG files and stick them into our model, which means that we have a realistic building that's in the model. It's not us putting some lines in CAD, it's actually the real drawings. So if there's chairs there, we leave the chairs there because they form an obstacle that we need to use to simulate. We can create our own geometries, as I've just mentioned, but they tend to look a bit less technical and not as good actually because we're not using the real drawings. And we can produce the specific populations, as I've mentioned, and quite often we get asked to try and model people in bars or nightclubs, which you can imagine is generally people that are quite intoxicated. They have no significance for their own safety, and that's something that we really struggle to try and model. So we try and reduce the pre-movement times, we try to reduce the flow rates of these people, and we try to make them go to places where they wouldn't normally go to in the initial stages. So basically one guy might wander over there first before he decides to leave. And these are the assumptions that we have to make as engineers. Of course, we have to visit lots of nightclubs on a regular basis to get a good understanding. What you see here is a little clip of some of the people that go in the model. The pink heads on the left represent the female gender, and the blue heads on the right represent males. We can have a whole array of different ages, weights, and patience levels. And we can actually put a rugby team in there if we wanted to, or a group of cheerleaders. And we'd have to try and obviously measure what the pre-movement time of a cheerleader would be in a fire situation. But it's just it looks quite simplistic there, and it is for the purposes that's necessary. And they've developed these little computer people now to look a bit more realistic. What you see here is just a building with contour maps And what the different colours represent is the likelihood of people being drawn towards a particular exit. And some of the advances in this model are actually amazing. We've got affiliation now, and I was explaining to some of the guys just at lunchtime, is that if one of you knows a building more than I do, and I'm actually with you, perhaps we're going to a museum, and the evacuation commences, then if I have an affiliation with you, and I prescribe what that affiliation might be on a percentage level, so obviously if we were partners in terms of husband and wife, then I probably have 100% affiliation. And what that means is that if you've got an understanding of that building and you know the layout and you know the exit route, then I will surrender my need to feel like I've got to find out myself and follow you with my 100% affiliation. Whereas if we've just met and we're very a low acquaintance, then I'm likely to go and pursue the exit for myself. And there's a whole load of behavioural characteristics which are starting to be incorporated in these models. And they're actually not being used just for fire and evacuation now. We've incorporated things like sight lines so that the person, wherever is stood in the building, can look and see a fire exit. Well, of course, lots of people in the marketing world clocked onto this quite quickly, and people like Sainsbury's now are using these to understand where they can put their signage for all sales types of systems. Airports are using this so they can better place the products that they want to sell to people. So it's starting to have a whole load of different applications now, other than the first principle, which was to look at helping us understand fire and evacuation. What this is just one of the models that we use. It's 2 floors of an office building, and it's just put into a virtual reality package, quite simply taken out of our original model. And it shows the people leaving in a virtual reality sense. Now, the reason these guys are sinking into the floor is that you see that there's a letter associated above their heads. And what that's indicating to me as the user is that these guys have got a particular amount of hydrogen cyanide in their body. And if they don't hurry up to that exit, they're going to, as this guy's doing, not make it. And all these little patches on the floor are actually the remains of somebody that tried to get out in a building. And I can interrogate each one of these in what's called the virtual reality morgue, and I can find out exactly why they died. And a lot of the time it tends to be people with lower pre-movement times. Now, pre-movement time is a term we use in fire engineering quite a lot, but what it means effectively is the time before, the period of time between the fire alarm actually going off and the time for you to commence your escape. Now, you guys will all probably say, well, I'd go straight away, but actually in reality you don't. You'll finish the meal, you'll finish your beer, you'll finish your conversation. And quite recently we did a test in our London office, and we found a pre-movement time of 1 minute in our office, which is fantastic time. And it was one of our group managers who was sat there, who was the last guy out. And the reason I know this is because we had the cameras in the office pointing on the staff. And I casually went up to him afterwards and asked him why he was the last one out of the building. And what he said was he was finishing his email. And that just goes to show that people don't move on the alarm situation. Even nurses and policemen and fire officers who are trained to react in emergency situations can have a pre-movement time in a particular situation of about 5 minutes. And that's something that we really need to understand, because that's something that's going to affect the likely choice of doors, the widths of the doors, the widths of the stairs, and all the other things that go into making a building safe. What we try to do is make sure that we get these people to die in this model as opposed to real life, as you can appreciate. This is just another application of the model, and it's something that I got involved in because I was a user of the model. I don't tend to use the model anymore, and I let our younger engineers or our graduates, who tend to be a lot more computational minded or gifted than I am, and they use this a lot more than I do. But this was back in 1999. We were approached by Ascot Racecourse, and they're doing a big redevelopment down there. And prior to the thought processes for the building, we were on board to look at the people movement assessment. And we can use our model actually in the non-emergency situation. We don't have to make people get out as soon as we can. We can give them a whole manner of tasks. And what I was looking at here, I was positioned in the Royal Enclosure with a video camera, just modelling the movement of people. And actually we can predict them now. And we've come up with quite a weird phenomenon that we found at racecourses. It's very much like the tide of an ocean, is that while the races are on, everybody's on the grass looking at the races. When the race is finished, people just retract back into the stands to either collect their winnings, to throw the paper in the bin because it was a disaster, or to go to the bar to get refreshments. Obviously, there's about 10 to 15 minute period in between races, in which case, once you've got your next bet placed, you come back outside. And this movement of people was amazing to see, and we videoed this. And you can see that top left-hand corner is just a shot taken throughout the summer's day, and this is throughout Royal Ascot. It's just one of the things that's really depressing about my job. I had to spend 2 weeks at Royal Ascot modelling the movement of people, one eye on the people and one eye on the horses. And what we're looking at here is just the distribution of people, and what you see down the bottom here is at 3:50 we were just looking at the movement of people after a race coming in and out. Then we actually modelled this in real life to understand how wide we can make our exits, where to put the rubbish bins, because there are obstacles that get in the way, because people don't just brush past the rubbish bin. If you're wearing a nice morning suit that's cost a lot of money, you tend to give yourself quite a wide berth, maybe 100, 200 mil. Well, that means that the bin might be 500 mil, 200 mil either side. That's maybe a metre or more out of our calculation, and a metre is a lot of exit width. So moving those bins is very important to us, which seems so superficial in the early stages of the design. This is another model that we use, and I'm going to come show you case studies of these models on some of the jobs as you saw earlier on. This is computational fluid dynamics. This is CFD for short, which is basically a tool that we use to understand the flow of fire and smoke in buildings. Detailed predictions, as you can see there. And we use it for more complex geometries. One thing I should mention is that we don't go straight to these models for the normal buildings that we design. It's only the likes of the Millennium Dome and the Battersea Power Stations of this world where we have a complex layout, open situations where there's a likelihood of fire and smoke that could affect people, and where we just really need to understand in a bit more detail what's going on. What we actually do is, say for this room, we divide this room in a three-dimensional aspect into a whole series of cells which would form little cubes, and there could be millions or thousands depending on the coarse mesh that we use or the level of detail that we're looking to obtain. And what we do with them cells is just calculate the standard PVT equations, because that's all really that it's about. We're just looking at the difference in pressure, volume and temperature, or the energy and the mass and the momentum, and they're solved simultaneously for each cell over a series of time steps. So effectively what we do is we set up the room, fill it with a whole load of cells, give it a prescribed temperature, which is the ambient temperature of the room, which I think this room is probably about 35 at the moment. Has anybody got any air conditioning on? Or we'll put the levels of ventilation in there, the door openings, things like this. And then what we do is we set a fire in that room. And we know that fire grows at a particular rate. And once we understand that, we can see what the smoke will do, where the fire will go in that room. Explain that. The internal environments are important, obviously, because that's the room we're modelling, but also the external environments are really important. So we have to take a series outside the room as our external environment, because the external pressures and wind and all the temperatures and everything else that are outside will affect what's going on inside this room, the pressures on the windows, and it will affect the way the smoke will actually flow. So what we're doing is building up more of a realistic understanding of the movement of air and temperature in the space. Now, top right hand corner is just a snapshot, a slice through. Does anybody know the Magna Centre in Rotherham? It won the Sterling Prize for Architecture, I think probably 2 or 3 years ago. And it was a conversion of an existing steelworks in Rotherham to an exhibition centre, learning and development centre. And what you see here, this cigar shape, this blob down in the bottom left-hand corner, was what they called the Earth Gallery, and it was a place where people would be occupied. And below that was was another aspect. And the fire brigade and the guys that were approving this were very concerned that a fire could grow and develop and stop people getting out of this Earth Gallery. And we did lots of tests. Temperatures of the glazing failure, the movement of people. But what I'm showing here is the simulation that we used to look at the smoke movement from that space up, and as it envelopes around the facade of the Earth Gallery. And what we actually demonstrated over these time steps, this thing might have been 15 minutes, is that we could get people out of there long before the smoke and the tenability criteria would be reduced, which aid our design and got a tick in the box, which is what we're trying to do for our clients at the end of the day, and also maintain safety. I mean, the obvious thing that we as engineers have got to do is maintain a level of safety. So I recognise I'm short on time and I want to get through quite a few things. So I'm going to show you some case studies now. This is, does anybody know this building? Has anybody ever been down there? I asked that question. It's a pertinent question because I spent probably half of the beginning of my career developing evacuation models for the anticipated 45,000 people that they expected in the dome. I think they got about a maximum of 10,000. In my heart, I know that it would have worked if 40,000 people had gone down there, and that's the important thing. An engineering success in my mind, but obviously I'm biased because I've worked on it for so long. Political nightmare. It was designed by Richard Rogers Architects. Bureau Happel were the engineers throughout the engineering disciplines, and I was responsible for doing most of the fire engineering. 12 masts on a cable net structure. It's not a tent, and it's not an umbrella. You couldn't breathe those words in front of Richard Rogers. What we have here is PTFE, which is a fabric. It's a non-combustible fabric. It's polytetrafluoroethylene, but more commonly known as kind of glass-reinforced Teflon. So you could fry your eggs on this thing and it probably wouldn't stick either. What you see there is the tunnel vent shaft. It gives you quite a good appreciation of the scale of this thing. They had no other way of erecting the 200 square meters of natural smoke ventilation at the top of this thing other than to erect scaffolding. And that scaffolding is erected up to 55 meters, which in terms of construction and procurement is pretty amazing. What this is my Exodus model, and the reason I use this here is because this is one of the core buildings inside the dome, and it was designed very prescriptively using the design guidance, and therefore the numbers of people on the topmost floor determine the sizes of the staircases in terms of a means of escape. So we went and did that, and it was all fine. And the client at the time, which was the New Millennium Experience Company, said to us, well, these are amazing buildings. Couldn't we increase the capacity on these upper floors for some kind of corporate hospitality? And we said, well, your stairs are restricting the numbers of people because they're physically built now, and the stairs are 3 at 1.8 meters. So from that, we can determine how many people they could accommodate. And they were toying with the idea of, let me just show you, just around here, they were toying with the idea of putting this link bridge in. What we set up doing is putting, I think it could accommodate 500 people this floor. We put 1,000 people in. And this is the architect's model. The red and blue dots, as I've explained before, and we're looking at the interaction of people here, which was important, because obviously the merging of flows, so I wanted to see if the first floor people would have an effect on the people coming out at the second floor. What we actually did was, should have a look at that again. We placed a fire in the top right-hand corner where the stair is, and what we're looking at basically, as you see down the bottom, is it's not playing at real time. Please, somebody obviously recognise that. We're looking at the people getting out, and what we need to demonstrate is that people can get out of this place before times for untenable conditions. Untenable conditions might be, again, parts per million of a particular product of combustion. It might be 2.5 kilowatts per square meter of heat radiation onto the skin, or it might be the visibility. If we can't see the exits, then that's obviously a tenability criteria. All of these might cause incapacitation or death, and it's something that we had to look into. And we sat around doing a sensitivity analysis in this building, and this is where the fire officer said, well, if this is corporate hospitality, show me how you've modelled a whole load of business people that have drank 4 or 5 bottles of wine. And that was the case. We set about trying to reduce the movements of these people and the way in which they'd conduct their escape in the non-emergency situation. I think we've seen that enough times. We took the model outside of the cores, so there's the core that you see that we just modelled, and these are the exhibitions. Did anybody go down there during the millennium, during the 2000? No? Not one hand. Hey. Well, you're the only person I modelled in this entire space for 40,000 people. And what this was really was just, it loses its aspect ratio slightly here, But they're all green because we're just reducing the size and the amount of information that the computer model needs to process. But the green dots are everybody, and we're just looking at thousands of people moving around one of the exhibitions, and we're looking at the interaction between the radial routes, the circumferential routes, and the adjacent buildings. This doesn't really show much other than a load of green moving squares, but there is some engineering behind it. CFD modelling, well, I explain what it's about in brief terms. This is the Millennium Dome, and this is some of the runs that I conducted using a program called CFX. We use this from the Atomic Energy Authority, and we had to use them in the initial stages because we just didn't have the processing power to run this model. So we had to go over to AEA, and they had the computational power to actually put this into a working model. And this is just a snapshot of something that we came out of it. What we actually did, which is not going to come up on your screen. Oh yeah, it is. This is a fly-through that we did with AA technology of the Millennium Dome. There's the tunnel vent shaft that you can see, the Blackwall Tunnel. Don't know if anyone appreciates that, but we designed the dome right the way over the Blackwall Tunnel, just because they wanted to encompass more space. This is inside the dome. The dome's 320 meters by diameter. It's 55 meters high to the roof. It's got 200 square meters of smoke ventilation in the center, and each one of those 12 masts can extract 50 cubic meters a second. And what we're modeling here is a fire, which is obviously again not growing at real time. The whole little pie down at the bottom is a snap of 30 minutes. What you're seeing here is the plume, the fire plume, which is the heat output effectively from a 15 megawatt fire. Now 15 megawatts really is just the energy output from the fire, but in real man's terms that's probably 2 articulated lorries burning at a very high rate. And what you see the downdrafts there actually is where we're actually pulling air through the mass, through the smoke layer, and it's a term in engineering we call plug holing, when we actually, you know, like you get in your bath at home, when you fill that with water, when the water drains through and it actually pulls air through as well, that's called plug holing, and that's what you get sometimes when you're pulling more air out through than you are smoke. This is a separate shot, and there's some other things that we noticed in our model here is actually the smoke came down a little bit. You see it bellows down in certain situations, and that was because the smoke was at lesser temperatures than the actual ambient temperatures up at high level. On a hot summer's day, we had temperatures in there of maybe 45, 50 degrees C. We had higher temperatures associated directly around the lighting rigs because there was these pylons pushing out all the lights. So we were actually getting higher temperatures from the air around them than we were from the smoke due to the air entrainment into the plume. I don't want to get too technical there, but what this effectively did was allowed us to validate our initial zone modelling, which were our hand calculations, and our understanding as engineers how we felt the smoke would behave. Now, I'm not saying that that's exactly how the smoke will be performed for a 15 megawatt fire in the dome, but I know that gives me a lot of confidence to understand how I think it might behave. And it helps me go to the approvers, such as London Fire Brigade and Greenwich Building Control in this case, and get it approved. Just a shot now, in case anyone's interested. I'm working at the moment with HOK Sport Architects to help them put this 26,000 seat sports arena inside the Millennium Dome. It's another engineering challenge because that big blob in the middle has just effectively taken out what we had as a mass of volume of space that we could accommodate smoke. Now that's been displaced by the arena, so we're in the process of doing some more scoping calculations now to see if that arena there is going to affect our 200 square meters of smoke then, which is that tiny little circle you see above the arena. So it's quite interesting, and it just goes to show that these models do get used in real life and real practical engineering applications. So quickly moving on, I want to look at structural fire modelling. What you see here is an office building, and what you see on the right of it is one of its columns after a fire. Now this was a building that was being constructed. It's called the Broadgate Phase 8 building, or Phase 8 fire, and it was one of the buildings over in the city. You see that white arrow coming in is where the fire occurred. And what happened here is that it was in a time in the construction period where it was prior to the application of the fire resistance to the steel. And by all books and all guidance and all we know in terms of conservative engineering, the whole thing should have come down. Probably not progressive collapse that we saw at the World Trade Centers, but we would have seen something local local failure in terms of deflection or something similar. It got the engineers, certainly the structural engineers at the building research establishment and the guys working on it, scratching their head and looking into the effects of fire on structures in more detail. And what this graph very simply shows is that our British standards have tests and temperatures that we apply to steel columns simply supported, i.e. we'll prop them up, there's the steel column or the steel beam, very simply supported, and we'll put them in a furnace at these temperatures, test them and find out how long it is before it fails, and then that column then has a grading that we can use in industry. But what we see by the blue lines is actually what happens in reality. You know, if a fire was to occur in here and if it was a fully developed fire, it would tend to break the windows, it would involve all the fuel, and we get ventilation coming in via the external atmosphere, which actually cools down the fire considerably. So whereas the red line is showing a consistent heat over a period of time that stays constant, what actually happens in reality is we get a peak of temperature and then we get a decaying period as the fire starts to die down. Now what that means is that we can actually show that real fire situations are not the same as furnace tests. As you can imagine, a furnace is probably 800 to 1,000 degrees C. If you stick anything in there, it's going to fail quicker than it would do based upon a real fire situation. So that we know that anyway. So what the BRE did, the Building Research Establishment in Boreham Wood, they constructed an 8-storey office building. They went ahead and replicated what happened at the Broadgate Phase 8 fire. And you can see the little Land Rover down the bottom there to give you a proximity of the scale. The right-hand top picture is the fire loading, which replicated a typical office, files, computers, desks, etc. And what you see down the bottom is an output of one of the facades where the fire came out. And, you know, would you believe it? It stayed up. And what we started to understand is that actually structures behave a lot differently as part of a 3-dimensional grid than they do as simply supported beams or columns in isolation. It makes so much sense that, you know, a column that's tied into 4 other columns and 5 other beams with a bit of wind bracing is going to behave a lot differently than if it's just, you know, exposed to elevated temperatures. So what fire modelling has led us to do, and this has come from the University of Sheffield, which I regard as probably one of the leading experts in the world in terms of structural fire modelling. And we've employed lots of their graduates and their PhD guys to work in our offices up north to do a lot of our calculations in terms of structural fire modelling. And they came up with this thing called Vulcan, which is finite element analysis. And really all that means is that we, like the CFD, we break the structure down into lots of different elements, look at them in detail, not in isolation, as then we start to calculate what happens for the next element and the next element and the next element, and we get a very good understanding of the behaviour of the structure in a fire. Lots of things will determine what causes failure from a structure in fire, but one thing that we do know is deflection. This is slightly exaggerated, but this is the deflection of a beam of a composite floor slab under elevated temperatures. So what we did is we partnered, not Greenwich, they're the evacuation guys, we partnered Sheffield University to look at and develop their model, and we've set up a company now purely looking at the issues associated with fire and structures. And here's a good model that was done recently for a composite steel frame building. And what we're looking at is the deflection of the floor slab under elevated temperatures from a fire below. And we can see that these things actually stay there for a longer period, I should say, than the British standard test would suggest. So what do we do with this stuff? Well, I can move on from that because that goes on for ages. The GlaxoSmithKline Beecham new offices on the M4 corridor going out towards Heathrow, they moved into this big blue kind of glazed facade building. And we want a fire engineering model for our work that we did on this. It's a composite steel frame that required 2 hours fire protection based on its height. CDM regulations, don't really want to touch on, but it's what happens it's the regulations which govern a building during its construction were important in this particular case. It needed 2.5 millimeters of intumescent paint, which is the protection that's used for steel. basically expands under elevated temperatures to form a protection around the steel, shield it from the temperature. And we used the Vulcan finite element analysis on it. We used the natural fire, not the British standard fire, so we're using real fire situations. We were able to calculate reduced temperatures of the perimeter beams next to the facade for obvious reasons. And in fact, we actually removed the fire protection that would normally have gone onto the facade. And in total, the 2 hours fire protection we reduced from 2.5 millimeters down to 1.3. Now what that meant is obviously we halved the protection, so there's an obvious capital cost saving there, as you're paying for half the amount of paint that you wouldn't needed in the first place. So there's a good saving and a good reason to do this. But some of the other things we did, it allowed us to apply the fire protection off-site, so that it all be prefabricated and brought on. Now I don't really need to go into the details of that why, you could ask me later if necessary, but it saved a whole load of time in the program, in the procurement process. Now cost savings are really important, but when you start designing buildings, if you can chip a week off the program, your client will be very happy and the contractor will be very happy, because it means it's a week sooner that he can move on to another site and carry on building, earning more money. So everybody likes reduced program. This helped it quite significantly. I say no overspray issues because when you're spraying intumescent on site, a case happened quite recently where there was a Porsche garage which was next to the building site, and they sprayed the structural steel with the intumescent paint, but there was a windy day. There was a lot of overspray that covered all these Porsches that were on the forecourt. Something that was a complete oversight while they were doing it, but you know, these situations occur. But it stops that. If you can have the off-site application, it's done down a factory somewhere where the steel's fabricated, then it just makes a whole lot more sense. And there's a picture of the building there on the right. You probably next time you're on the M4 going out towards either Wales or Bath or Heathrow, wherever you go, and you'll probably see that building, and you'll be able to say, I know someone who won an award for that building. If you want to do that. I recognise I only had half an hour, so I'm probably getting up towards the end of my time now. And what I want to say is that these are just some of the practical applications and some of the good things that we've done with our computational models in terms of fire, for structures, for the movement of smoke, and for the evacuation of people in buildings. And is it the final answer? Well, actually, no, it's not. And a lot of people have probably told you this over the course of today, but it's just another tool that we have. This is there's a hotel in London, Clerkenwell Hotel. It's 5 stories. It's got a single staircase for its means of escape, which if anybody knows the design guidance is a complete no-no. Any building constructed over 11 meters needs 2 means of escape. So it's got a single staircase, and it's balcony escape, which means it's going across an open atria. And everybody in London basically raised their eyebrows at this and said it would never work, and it was a risk. But we were determined to demonstrate that we believed that it was fundamentally safe. So we did a whole load of work using our CFD models, and this isn't a moving image, unfortunately. This is just showing a slice through a section through the building and looking at the 5 meter ISO surface of the smoke. Basically, anything that you see in that blue blob is effectively less than 5 meters visibility. And we set about it, and we were quite confident that this is how we thought the smoke would move in the real life situation. Of course, what did London Fire Brigade ask us to do? Well, go ahead and show us. And we couldn't obviously light a fire at the bottom of this atria once the building had been fitted out. So during the construction program, we had to, with the contractor, semi-fit out the hotel to represent a bedroom, a balcony, and the atria, and actually look at how the smoke and heat would move from a fire in the bedroom. What we've got there is a 40 kilowatt heater that's blowing out heat into the metal cylinder on the right, and the tube that goes from these 2 little smoke generators in the bottom take the smoke up into the cylinder. The heat is mixed in with the smoke there, causing kind of like the centrifugal effect to get it all mixed in and then pushed straight out into the atria. And the smoke's really just there just to give us a visual representation of how the heat's working, because obviously you can't see the heat waves from the heater there. We actually originally, you can see, we used 80 kilowatt heaters, but they were too powerful and just blew everything straight across into the opposite bedroom, which was something we found out on site. So you can see what's going on there. That's the balcony, and that's the smoke that would be coming out obviously from the top of the door up into the atria. And I've got a movie clip. It's 15 minutes long, and I wouldn't ever want to bore you with that. But this is just a snapshot of how the smoke behaved as it came up. And London, there was 5 representatives of London Fire Brigade, and there's probably 15 other people that were representing health and safety representatives, basically. And they tried every which way they could to get this to fail. They put baffles in the way. They increased the heat, reduced the smoke, all kinds of things, sensitivities wise. And we all walked away at the end of this day with a tick in the box. So there's a 5-story single staircase atria balcony escape hotel in central London that's been approved. We use computational modelling as our 3rd level of validation from our initial thoughts and our hand calculations, but we did have to, in the end of the day, go out and actually prove that it works using real life situations. And hopefully that has given you some appreciation of fire models in the fire engineering industry. Thank you very much.